G'day guys, got an SD2100 that has come in for repair, and this is an interesting repair, and this is common to how these things stop working, and I'll give you a bit of a rundown how to increase the performance very easily and fix the faults in these. They're usually very similar when they stop working, what the faults are. So this one came in, basically wouldn't receive anything. It was deaf as a post. So one thing you do have to remember with all these detectors, and I'll have to spin this around so I can get a bit more of an angle on there. Oh, I don't know if you can be able to see. But this wire here with that is used to screw this MOSFET to the case, is what you use as your ground, which is positive. I know that upsets people, but it's connected to positive because to generate the rails on this detector, the voltage rails, it uses positive as a ground, it uses negative as negative voltage, and it has a switch mode supply here consisting of a there is a oscillator or part of the circuit here. I shouldn't even say it's derived off one of the ICs here. Can't remember off the top of it. I think it might be this 273 that's here. It generates 62 or 64 kilohertz signal, comes down here. That's a 4093, and through various gating and outputs, it drives a MOSFET and a transistor for memory. On this one, I think I've got to actually check, make sure it's got both devices, because the earlier ones only had a MOSFET for memory and a series regulation transistor. But anyway, the way this works, it has an inductor here which is 150 microhenries, and it oscillates away. It's got a diode next to it in here. I've got it on at the moment. I actually have repaired this. I was going to run through the repair, but just stating how it works. I just need something to point. So if you want to fiddle around with these things, this point here, if you have your multimeter lead or oscilloscope lead onto the positive as a negative, right? Just think of that is now negative, and you got the negative is minus 5 volts. This point here, you will measure plus 5 volts. So if you actually measure from the negative, as in the battery negative, to here, you'll measure 10 volts or a little bit above. So you've got to use the positive as your ground, positive to ground, like a pommy car. So, oh dear me. We've all had this cough. It comes and goes. I don't know what it is. It's not COVID, but the kid brought it home from school, and we've all had it ever since. It's slowly going away, but yeah, occasionally it builds up and it gives you a tickle in the throat. Damn. Just make sure it's not going to get me while I'm doing this. Okay, this comes through. What actually on this detector, you got the input stage here. There's normally a ZVN44 something or other. Can't remember the number. They're all covered in white paint, so I don't actually see the number all the time. I'd have to go and look at the schematic. But that's an N-channel MOSFET sitting here, and there's a P-channel one there, and your first stage differential amplifier is the LM394, which is this one here. 9 times out of 10, this N1 that sits here is the one that dies. And depends how it dies, it can take out the P channel, and depends how that dies, it can also take out the base transistor connection of this device here. But we're lucky because on this one it had a leaky front end transistor. I only found this after I fixed the fault, but I had to replace this 4093 that drives the gates of this, the P channel and the N channel MOSFETs, that had died. And the reason it had died is this capacitor that was here. These go partially short circuit, and that can also take out this voltage monitoring. It's a BSS 170 for memory there, and you replace this capacitor. This is common on all the SD series. This capacitor here, I don't know why, it's the only one that goes leaky, and it's just a ceramic. So what I've done, I flicked it out and I put a 10 picofarad ceramic capacitor there. Nothing's fantastic, but this is connected up on, I think it's pin 2 on the 4093, and it should have a relatively sort of square wave shape on the waveform there. And if this has gone down, the waveform here is all squashed up. Now, when this doesn't get its signal, and also if it fails, and there's also other mechanisms for that will cause this to stop working, it locks the gates of the P and N channel input FETs here. It locks the gate of the N channel down to negative, and it locks the gate of the P channel to positive. That turns these off. No signal can come through. The easiest way to test to see where the fault lies, if it's in the switching or wherever, I have to turn the oscilloscope on for this. So I've got the oscilloscope connected. You can see the connector there. It's connected to positive. No, I'm going to have to, well, it's going to be hard to do actually, because I have to point at the detector with the camera and also at the oscilloscope. Okay, I'll give you an idea of the waveform on pin 2 here. I'll get onto him first. Okay, then I'll have to work. I wish I had 3 hands. Hang on, I have to loosen this. This is going to be hairy, scary. But if you look on, I'm on pin 2 of the 4093, and that's the waveform that you want to see there, not bouncing around like that. But you can see it's attempting to be square waves. It doesn't have to be accurate when it goes in here, because the 4093 wave shapes that signal, and it squares it up quite nicely. So what it basically is, it's generating the on and off pulses for the 2 input MOSFETs in antiphase. It's just square waves 180 degrees out of phase, which control the timing. The small capacitor that goes leaky, that is there for a bit of delay between switching cycles. You can change that from 10 picofarads probably down to 1 picofarad, but it may introduce noise into the receiver. It's something you could play around with. So that's that waveform there. If I just do that trigger, and it's going to behave itself now, is it? Oh, okay. No. Yeah, I've got it on low frequency reject. I should actually probably have it on high frequency reject. It would be more stable. But if you can see that, that's on pin 2 of the 4093. I'll just go back in so you can see that there. Now, the other thing to look at, it's the capacitive coupling of the probe causes that to happen. I've got this thing on. So what we can do now, let's have a look where that input MOSFET was. I've replaced it. I put in a the same as what they put in the GPs and GPX. It's a better MOSFET. It has lower on resistance, and the gate capacitance, drive capacitance, is still pretty low. So if I remember, which is the gate, which is that, and it'll have a hernia. Hang on a second. I'm just going to adjust this. So I don't want it flicking around. Or where's my trigger level going? Yeah, no, we'll be on HF. Yeah, so that's better. Okay, I'm just touching it, not touching it, so it's going to do a little bit of a crazy. Okay, this is the N input channel, and I've got to get back onto the gate. I don't want to slip and short it out. That will be embarrassing. But if you can see the waveform there, that is the input on the gate of the N-channel MOSFET, which is driven by the 4093. Well, there you go. So that's what you've got. That's your timings. That's just me slipping off the connection. So that's what you want to look for on the gate of the N-channel input MOSFET. Now, I should have two probes hooked up so you can have a look at the antiphase on the P-channel one. I'm on the gate of the P-channel one, and basically it's a mirror image of the N-channel one, and that's also driven off the 4093. So go back down. You can see where I'm poking if you can. I don't know if you can actually see that where I've got my fat fingers and fat oscilloscope probe, but yeah, it's a middle leg of that transistor there. I'll take it away slowly so you can see that one there. It's the middle leg's the gate on that. Now, as you can see on here, if I go on, now I've changed the resolution or the time base of the oscilloscope, but that's the signal on that capacitor that goes leaky. That's what you want to see on that, and that also is the same signal. It always does that. I'll shut that up. Yeah, and that's on pin 2 of the 4093. It's the same signal, and it's hard to tell under all the white paint. But these are your failure points. These are what fail. The other thing that gives up the ghost, these two N-channel MOSFETs here, they're your transmit drivers that drive the transmit waveform into the coil. These can die. This has had work on it before under this tape. You can see some bridging wires in here, and this one hasn't got white paint, which obviously means it's been replaced. And I've checked both of these. These are fine. The other thing that dies too, it's got a comparator here. That one there is a comparator, and what it does when the flyback voltage gets back into the system, you've got a series diode here. These things are pretty robust. They're a Phillips thing. I think they're rated at an amp or so, 250 volts. Just a fast diode, and the flyback voltage comes through, and with the comparator, this big capacitor that you don't touch the bottom of this because it wants to zap you, because it'll have around about 190 volts across it, and it's pretty sizable, holds a bit of energy. And I'll just point out some other things too. The resistors, now I'm getting around the nasty end of the detector, so I've got to be careful here. The resistors here, these two resistors are the bleeder resistors across this capacitor, this one. If these go open circuit, the voltage will not bleed off and you can get zapped at any time in the future if you touch underneath or you touch this thing here. This is basically set up as a resistive regulating voltage control, that it limits the voltage from the flyback to around about 190 volts, 185, something of that nature. These also die. That's just an NChannel MOSFET, 200 volt rated, probably rated for about 3 amps or so. Nothing fantastic. And same with these too, nothing fantastic. Yeah, so the other thing to be wary of, this is another failure point in this detector as well. Now, well, you can't see behind those capacitors. If I turn this thing off, I'll just point this stuff out. So I don't want it to be on and start giving me a whack if I grab it in the wrong spot. But yeah, I'll get my hand under here is safe. It's all low voltage. I'm not going to go and touch the wrong thing. But you want to check these two resistors here, and there. That one, and that one. These are both 100,000 ohms, and they are in series, and they are connected to the capacitor here. They got high voltage on these, and that drops it down, and it's got a voltage divider here. Oops, can't see. It's a voltage divider circuit here for a couple of resistors, and it goes into the comparator. If the high voltage is not available, the comparator will shut down the transmit here. I think it's a 40106 for memory. Haven't replaced these. Anyway, I think it is. It's a 40106. It's a hex inverter that drives these two transistors here. One's a PNP, one's an NPN, and that just flip states the drive to the MOSFETs, turning these MOSFETs on and off. There is also another comparator input from this BS170 that's connected up onto the transmits stage. Signal from the transmitter comes through this capacitor, turns this device on. It goes back into the comparator circuit, and there's a few little ancillary components around there, and that also governs the 4093. If there's any fault in the system, the 4093, I just want to make sure that this just came up with said low voltage, low power mode. I hope it was still working. But any faults, this will clamp the input stage into an off position. So yeah, got to be careful working on these because of the high voltage, the high DC voltages stored in that capacitor there. But anyway, that's this one fixed. I put a 2SK 1334 in here as a replacement for the one that was there. Far more robust MOSFET, and gives better performance for the detector. You can replace this P channel, but the way it's set up, this is from memory. I think it might have a resistor in the gate circuit that doesn't allow much current through, and if you put a different device there, it might have too much gate drive capacitance requirements, and it may not turn on and off fast enough. But I'll have to go and recheck my notes on that. You know, it's hard trying to remember everything about these detectors as such. So yeah, you can check your signal. You got LM394 differential, just 2 transistor log amp differential amplifier. You got associated biasing here. Couple of resistors, little transistor. On the collectors of this, you've got a couple of parallel resistors, and that supplies current through this device. Those resistors are then tapped off. I think it's 5534 here, NE5534 as an amplifier stage, another 5534 as another amplifier stage, and here you've got the signal going into the integrators. This one here is just straight through amplification, and the output of this one goes to this one, inverts the signal, and that's how it does all its subtraction to get rid of the ground noise and set up your channel 1 and channel 2 inputs through filters and so forth. This is just audio around here. Power supply area here. You got fine tune for frequency. You can change these jumpers here, either both of them hard over that way or hard over this way. Don't muddle them up and do it half cocked. It will burn the detector out. It's just the way it's set up. So it's pretty pedestrian. It's that's a EEPROM here, which basically has the timings for the transmit receive cycles. Well, they're all derived off the transmit. So down here generates a signal through this to the power supply to run the oscillator to generate the positive voltage, which is 5 volts above battery positive. That confuses everybody, but that's how it works. There's not much to it. You got your resistors in here as your damping circuit for your coil that brings down the back EMF fast, so you get the receiver on faster. You got to have that. Just having the clamp circuit won't cut the mustard, as we say. You got to have this, closing off that back EMF energy relatively fast. And when that's gone, these turn on, let the signal through, gets processed through here, and you hear it. So channel 1, channel 2 ground balance pots, channel 1, channel 2 switch. All that does is switch the audio. It doesn't actually change anything on channel 1 and channel 2. It's just it's got a switching circuit here. It just selects which goes through where. It's just an audio switch. I'm trying to make it probably sound more complicated than what it is, but it's just an audio switch. And when it's in the middle position, so nothing is biased on or off, the greater amplitude of either channel 1 or channel 2, because they use the long pulse as a channel and the smaller pulses as another channel. The greater amplitude of the signal coming through those is selected, and it will come out in the audio. You won't hear the other channel when, if 1's activated, you won't hear 2, and 2's activated, you won't hear 1. If you ever hear it, I'll tell you, this is a little bit of a good thing to remember. If you ever hear a signal that is down dipping, usually means it's not usually anything but big deep gold, right? And if you hear the one that goes whoopy whoppy whop like this, it makes sort of a warbly sound. We do call it the warbler. That is a target which is large enough to trigger both channel 1 and triggers channel 2, and the detector can't make up its mind with its switching arrangement what signal it's going to allow through. So it goes like 1 2 2 1 1 2 2 1 back and forth like this. And if you ever hear a warbler, definitely dig it, because 9 times out of 10 it'll be a decent size target. It usually will not be clay. It won't be any sort of conductive clay. You could possibly get charcoal to do it, but I've never ever found that by using these old detectors. But when I get the warbler, you know, warblers to me sometimes, what can we look at? Using the 18-inch coil, it'll warble on 1 ounce and up, and the larger the gold, with also the increase in depth, will keep that thing warbling. If it's closer to the surface and it's large, it's still will just activate channel 2 in most cases. So it's going to be a fringy type signal, and the detector sort of gets a little bit confused on it. Well, it's just going one channel to the other, and very quickly as you sweep the coil over it, because you're getting a bit of a difference, in the signal to the coil, and it just makes this warbling sound. And I'm not really sure if the newer detectors do. I never heard a warbler with a GP or a GPX. Most of the big gold I got was with the older detectors, and the 2000 was the one that used to get my big gold. It's probably because I haven't been out using the new detectors with monstrous coils. I have got a 20-inch and a 25 mono. I should get out there and use a modified GPX 4500 with that coil. It might be quite interesting. Anyway, I think I'm pushing the limits of my battery on this, because it did give me a low battery warning before. That means I've spoken to too many people on the phone usually. Nothing else I can really say about this, except if we turn it on, there it goes. It's on the cancel coil, so sometimes they sound a bit strange on the cancel coil. It's just a little bit of funny phasing effects on the coil. But if I get something, whoops, there we go, some piece of aluminium and go near the coil, as you can tell, it's a worker. So the customer's going to be happy that he can go out prospecting. Let's try my 0.1 on it, see if it actually picks it up. I mean, Jesus, that's not bad, is it? Picks up a 0.1 on the cancel coil very easy. I'm about 3 inches above it, but it's a cancel coil. And I'll try a 0.05. Not a hope in hell. Oh, dear me. It's not going to pick that up, but it picks that up okay. So anyway, that's that. A little bit of power line interference coming through, because that coil isn't locked in the middle. It's a bit skewed off, but you can hear the way these drift, because it's an LC oscillator. Don't know if you can hear that. I'll turn it right up. That pulsating sound. That's 50 hertz, and if I wave my hand over it and put a bit of air over it, it'll change. Or even better, these capacitors here, which you can't see, there we go. These set the frequency anyway, around here. There you go. I've just changed the capacitance value by freezing them a little bit, and there's the 50 hertz. It's matching the amplitude of the 50 hertz and generating a signal. So that's just power line interference. I better blow on it and heat it up to where it was. It was quiet where it was. So there you go. That's why all the newer ones have crystal oscillators, so they don't do that. Actually, they're still very cold. Yeah, I shut them up, put my finger on them. There you go. It will change the value. You can adjust this pot here too to fine tune it. If you get near power lines, you can fine tune these because it's a lock single frequency detector. So you just tune the power lines out and then you go detecting. There you go. She's getting back to where she was. Okay, that's all I'm going to do because I think the battery's going to go flat. Very, very simple detector to work on. There's nothing fantastic about it. You know, some of the chips probably a little bit hard to get now, but you know, like things like 5534 op amps and that, which this is full of around this area here, and just some 4000 series CMOS. I think that's a 273 for memory. But like I say, I have to check. The comparator is a I think LM311. Yeah, just be careful of the high voltage. You know, just be careful of high voltage on these. That's what I'm saying. You got to be careful. People, there's no labeling on the detectors. There's nothing that says, "Oh, warning." You know, don't pull it apart. You're going to get zapped. You know, you'll pull it apart and get zapped. Even on new detectors, right? High voltage is stored in these capacitors. Just be very careful. You know, you don't want to touch it. It will give you a boot and a half. So I always want to stress that. It will give you a boot and a half. The only thing I hate about this detector, this design, I'll turn it off, turn the noise off before I go. I should point out is that the adjustments here. Can I zoom in a bit? There we go. Have a look at that. They've glued. I don't know what happened with this design, but that is just glued in with some sort of Scholastic. All this business. And that's your adjustment to get rid of earth field. But yeah, if anything come adrift under there, you know, be a hard fix. You probably end up pulling pads off and stuff. But anyway, yeah. Oh, the other thing too, there's a lot of stuff I just remembering about working on these things. These are tantalum capacitors. They're all through the detector. They're good, but they can play up and they can change value. The way the tantalum just fractures inside, and it can actually cause noise in the detector. And also, they have a bad habit of going short circuit, right? So they can take the supply rails down and you go, oh God, I've got a short circuit. Always check the tantalum capacitors, right? They're a good capacitor to use for this because they are a low impedance capacitor. They keep the noise down, but it is what it is. Anyway, catches. See ya.